Hi everyone, I got cut off on my last video mid-sentence, so we're starting another one. So with this example that I have depicted in this picture, think about someone on a moving train. It doesn't have to be on top of the train like these two people, which you shouldn't be on the top of the train like these two people. But if you're on a train and that train is moving and you're walking, your velocity from the perspective of someone on the ground is whatever the train's is plus your velocity. So resultant is the combination of both of those. So now let's look at a couple practice problems. A baseball is thrown a distance of 20 meters. What is its speed if it takes 0.5 seconds to cover the distance? So we're looking for speed. So we'll write that with an S. And speed is the distance over time. So our distance is 20 meters. And it takes 0.5 seconds to complete that. So when we divide those, we will get out 40 meters per second. 40 without a decimal point here is correct using sig figs. It's only one significant figure. Both of these only have one significant figure. No direction necessary because it's a scalar quantity, speed is, because we're looking for speed here. Okay, and this is average speed. Even though it doesn't say find the average speed, what we just found, it was the average speed. All right, number 2, if it takes Ashley 3 seconds to run from the batter's box to first base at an average speed of 6.5 meters per second, what is the distance she covers at that time? So let's set up the formula. Average speed is equal to distance over time. We know that her average speed is 6.5 meters per second. And that is equal to the distance she travels, which we don't know, divided by 3 seconds. So we use algebra to undo things. We're going to multiply 3 seconds to both sides so that d, distance, is by itself. So when we take 6.5 times 3 seconds, we will get out the answer of 19.5 meters. And if I think about sig figs, I have 3 seconds and 6.5 seconds. Multiplication and division rules state take your least take the least number of sig figs, the least precise number of sig figs, I think is how I worded it, which is 1. So I have to round it to right here, which would be approximately 20 meters. So notice there's no decimal point, and I did write the approximate symbol right there. All right. Number 3, Bart ran 5,000 meters from the cops and at an average velocity of 6 meters per second north before he got caught. How long did he run? So this is a velocity, average velocity. So we do need a direction when we have our answer because it is a vector quantity. So let's look and see what we're trying to find. How long did he run? Well, time is not a vector quantity. It's a scalar. So we actually don't need to worry about a label that involves a direction for this one. So we'll just calculate the average velocity or use the average velocity formula to calculate this. So average velocity, is the change in position over the change in time, or just time. So for us, we know what the velocity is. Let me use a different color here. 6 meters per second. It says north. I'm not going to write that in my calculation, though. It says he ran 5,000 meters. Hopefully that's only in the northward direction. Otherwise, we can't calculate this. So we're going to assume 5,000 meters north. And we are going to divide by our time. So to figure this one out, I would have to multiply time to both sides and then divide 6 meters per second to both sides. So essentially what I am doing is to find t, I have to take the 5,000 meters divided by my 6.5 meters per second. And I will get out a result of t equals 833.33, and then that repeats. So I look at my sig figs. Since I'm using multiplication and division, I use the least precise number of significant figures, which is 1. So I will round to right here. So that would just be 800 meters. And I should have an approximate sign right there. A few more problems. Number 4, metal stakes are sometimes placed in a glacier to help measure the glacier's movement. For several days in 1936, Alaska's Black Rapids Glacier surged as swiftly as 89 meters per day down the valley. Capitalize that. Find the glacier's velocity in meters per second. Remember to include direction. I have some typos, it seems. So let's look at what we first have. We have 89 meters per day. I eventually want that to be meters per second, way over here. So it looks like my meters are already set. I don't have to worry about those at all. So I need to change the days though. So we're going to multiply by a few things. So I'm going to multiply by something that has days on top, and I would like to know seconds on the bottom, but maybe I'm not that knowledgeable. Let's kind of break things down a little bit. What do I know another time that takes up the same amount of time as a day? Well, I know there's hours in a day, and there's 24 of those. 24 hours in one day. So the day and the day will cancel. Well, it's still not seconds here. So do I know how many hours are going to give me seconds? Well, no, I don't. So what else do I know goes into an hour? Minutes. So I know in 1 hour, there are 60 minutes. So the hour and hour cancel. So now my label is going to be minutes, but it's not seconds yet. So keep going. I do know how many seconds are in a minute. That's 60. And that's my last label to cross out. Oops, that should be the minute crossed out. Everything's crossed out on the top except for meters, so that will be my new label on top. Everything's crossed out on bottom except for seconds, so that will be my new label on the bottom. So what I have to do is take 89 times 1 times 1 times 1, divided by 24, divided by 60, divided by 60. And when I do that, I get out a pretty small number. That number in scientific notation is 1.03 times 10 to the negative third. And for sig figs, the only number I was given was the 89. So this was all multiplication, so I have to go to 2 significant figures. So this really should be 1.0 times 10 to the negative third. So very, very tiny. And this is approximate. All right, let's try one more. Let's see how much time we have for it first. Yeah, we can do it. All right, a comet is cruising through the solar system at a speed of 50,000 kilometers per hour for 4 hours' time. What is the total distance traveled by the comet during this time? So speed is distance over time. I know what the speed is. It's 50,000 kilometers per hour. It's traveling for 4 hours, so I don't know D, but I do know that the time is 4 hours. And I need to find D, so I just need to move this next to the 50,000, which I can do through multiplication. And when I do that, I should get out 200,000 kilometers. And check my sig figs, 1 sig fig here, 1 sig fig here. It's multiplication, so I take the least precise. So that's 1 significant figure, which I have right here. So there we have it. All of this was using the velocity and speed formulas. Lastly, I want to point out these 2 graphs we had last time that we're calculating distance on. When we calculate the velocity on them, the velocities are going to be the same, except this one is positive and this one is negative, because it all goes back to the final minus the initial. And in this case, the final was bigger than the initial. So take a look at those and make sure you understand why this is negative.